Hello, welcome to another AP Daily, and another episode of AP Daily. Today's topic, I guess, is going to be most closely aligned with Learning Target 5.5 with the College Board. And the main topic is going to be an intro to kinetics using collisions. And I'm calling this daily video number 0. And we're going to cover a broad overview of kinetics using the collision model to explain how chemical reactions occur. I'm so happy you're here today. My name's Tucker Basil, and I teach AP Chemistry at Chaska High School in Chaska, Minnesota. And I'm not here with the College Board. Instead, I'm here with the off-brand, or the non-name brand, known as the High School Plank. Right, so first thing I want you to do is to consider these two equations. Just look at them, think about them, see how they make you feel. Now that you've done that, I want you to think about what can you tell me about them? What can you know just by looking at these? It's going to be quiet here for a second while you think about that. Okay, that's 5 seconds of thinking. And hopefully you were able to come up with some things. If you haven't come up with anything yet, pause it and really think about this. I want you to try it. But hopefully you can come up with something, right away that you notice that, hey, the first equation, the one in the green, you notice that they're all gases. Hey, good job, you noticed that. And same for the blue one, the second one, they're all gases. We can also tell that, there's hydrogen and bromine involved in the first one, and oxygen gas as reactants. And then they're producing bromine gas and water vapor. And the first one is, a nitrogen-oxygen compound and carbon dioxide reacting to form nitrogen dioxide and carbon monoxide. There's a lot of things we can tell from this. But now what I want you to do is I want you to consider this. So consider just the first equation. And what I want you to think about is, how does this reaction occur? How does this reaction actually go about happening? And so when you're thinking about this, so you're thinking about how does hydrogen and hydrogen bromide or hydrobromic acid, how does that actually react with oxygen gas to give us these reactants? So specifically what I want you to think about is, how does what's on the left here, how does this become that? Because it's really not just 2 molecules that are reacting here, right? It's a total of 5 molecules, because we have, if we think about it in terms of if one reaction were to occur, how do these 5 molecules become these 4 molecules? So again, I want you to pause and think. I'm going to wait about 5 seconds, and I'm going to think about this myself. It's a little tricky, right? How do the atoms actually rearrange themselves to become the product? And so maybe before we get too crazy, because this one's actually a little complicated. The actual mechanism in which this occurs is a little complicated. So instead, let's go to this one. In this case, we only have 2 molecules on the left, and that becomes 2 molecules on the right. And so feel free to pause now, but I'm gonna go over and show the particle diagram for this, and even some Lewis structures for this to maybe help you visualize this a little bit better. Okay, I've got this. So I drew this picture for you, just you though, nobody else. And so in the particle diagram, we can see that. So we've got NO, and that's what this first diagram right here is, or this first molecule, and then that's reacting with carbon dioxide, this guy right here. These 2 molecules are rearranging and becoming these 2 molecules over here. So NO2 would be this first one, and CO would be the second one. So the question is, through what mechanism, how do they actually go from being what's on the left to being on the right? And so again, I want you to think about that. I also included the Lewis structures off to the side, though that's not super important, but maybe that's better for you to visualize than just a particle diagram. hopefully at this point you've come to you've noticed something. And I'm going to start drawing on here. So I'm going to switch the way my camera is presenting so I can draw on my screen better. All right, I'm over here now. Okay, so now hopefully you've been able to notice that when this reaction occurs, what color would be good? I guess blue. When this reaction occurs, you notice that this oxygen right here is going up and attaching to the nitrogen, right? This oxygen right here is going swoop up to there. We can almost imagine that oxygen floating up and attaching itself right there. And if we look at the Lewis structure, we can see the same thing. We've got this carbon-oxygen bond here, and somehow that's being broken. And this oxygen is coming up over here. And now, on the right-hand side, it's probably this one over here. It's probably this oxygen right here. And it's becoming attached to that nitrogen through a covalent bond. And so the question again, and so it would be like this one right here. So the question again that I pose to you is, how is this happening? The oxygen isn't just going to float up there, right? Hopefully that's not what you're thinking. But I mean, if you did, I guess that's wrong. But the oxygen isn't just magically going to float up there and just boop, appear, right? There has to be some sort of physical means in which this happens. And so the way that this actually is going to happen is through a collision. So you can imagine that this molecule is going to collide with the molecule on the top, and if the conditions are just right, that oxygen is going to whoop and attach itself to that nitrogen through the means of a collision. And so that's one of the requirements that there needs to be in order for this reaction to take place. Now there are two other things that also have to be have to be in the right conditions in order for this reaction to take place. But the collision is the first one, and then there's two other requirements that have to get met. And so what I'm going to do now is I'm going to show you two different animations to help you get a better understanding of that idea. Okay, so before I show you the video, or before I show you the simulation, what I'm going to be showing you is this reaction, and we're just going to, instead of like having actual element names, I'm just going to keep it simple and general, and talk about just, we're going to have one atom reacting with a molecule, and then we're going to get a different molecule and an atom out, single replacement. And so I'm just going to represent as R and B and G, so red, blue, and green. And so we're going to see this reaction taking place. And I want you to remember that there are going to be three things that are requirements for the reaction to occur. So the first one, I want you to write this down. So the first one is that there needs to be a collision. Second thing, and third thing. So we're going to leave space for that. And then the other thing that I want you to observe in this simulation is, what other interesting things do you notice? I'm going to come up with at least two things. Maybe you can come up with more though. All right, so here we go. Video time. All right, so here's our simulation. So I encourage you to watch this at least a couple times. And when you do, you just follow like a particle around and notice the reaction actually taking place. Sometimes it happens quickly and you might miss it. So this over here on the right hand side, if you're curious, that shows the concentration or the number of particles. And so we notice, hopefully you're noticing, that we're getting more of these other particles that are being created, and more lone blue guys and less of what we started with. So if I rewind this, go back to the beginning, you'll notice that the initial conditions are such that we have the red and blue stuck together, and we have the blue and green stuck together, and then the red just by itself. And then when they say enable reactions, wait for it, there. Now the reaction can start taking place, and you notice immediately in this general area a reaction occurred. So again, you just like follow like one of the particles around and just see what actually happens. I'm gonna let it play all the way through, and I want you to rewind this at least a couple times now, and follow a particle along to see if you can see the conditions. So there are two conditions that need to be met in addition to there being a collision. Okay, I don't think that there's going to be any more change that happens if my memory serves me correctly. But what you should have noticed is that, first of all, yeah, the collision has to happen in order for the exchange to occur. And then secondly, the other thing that needs to happen is that they need to be in the right orientation. So if, when this is happening, if they're not oriented in just the right way, the reactant and the two reactants could hit each other, and nothing would happen if they're not oriented the right way. The other thing that has to be true is that they have to be moving at the right speed, or they have to have the right amount of energy in order for this to happen. So if they're, just booking along and they hit each other and it's in the right orientation, bingo, 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 you got it. If they hit each other and not moving fast enough, or it's not oriented right, the reaction's not going to occur. So let's go back over to our list here, and we have to have the correct orientation. I don't think that's spelled right. Either way, whatever, you get the idea. It has to be in the correct orientation, and have to have enough energy, or speed is what we observed for that. And then anything else interesting that you noticed would be worth noting. You may have noticed that these were gas particles. These are gas particles. So if you think about kinetic molecular theory, they're going to move in a straight line until they hit something else, and then they keep going. The thing that makes it so it's not an ideal gas, though, is that they do actually interact with each other and they react. They're gas particles, and then this is worth noting. I didn't write it on the left, but you hopefully observed this, is that not all collisions equal a reaction. That is worth noting. All right. I see that this video is starting to get long, so I'm gonna we're gonna pause this video. Let's see if I can do this. There we go. Hey, I'm bigger now. So I'm gonna pause the video now. Well, I'm gonna end this video. I'm gonna do a second video, in which case we're going to I'm gonna show you a second simulation, and then we're going to see some other interesting things about the mechanisms in which reaction occurs. And then we're going to I'm going to give you guys some rules and some things to consider when doing this, and then talk a little bit more about the study of kinetics. But before you go, I have a Laffy Taffy, and I'm going to read this to you. I haven't read them yet, so this will be fun. All right, you ready? What does a ghost call their partner? I'm not sure. My boo. Hey, boo. All right, second one. What did the net say when the ball swished in? I don't think I know this one. That's my internet? Okay. That was thank you, Laffy Taffy. That, as always, one of them was good. The other one was a little bad. All right. Thanks for watching, and I'll see you in the next video where we do a little bit more exploring of the collision model of kinetics.